Hello everyone and welcome back to this next lecture in the DC to DC converter series, and this is where we had left off, where we were building the magnetic model of a 3-winding transformer. So we had written all the equations of how we can calculate the currents for the flux linkages, and we had calculated the flux linkages from the induced EMF. Now in this lecture I'm going to complete this simulation model and run the simulation. So as before, let me just collapse this so that I have a little more space. As we had already seen in the last lecture, solving these equations manually resulted in these extremely messy equations, right? Because we had to express each and every equation, or rather current, in terms of the flux linkages, and this was all by manual calculation. The recommended way of doing this is by representing these equations as a matrix equation, and by solving this matrix equation, and the method of doing that is by converting this matrix L, which is a square matrix, to either the upper triangular or the lower triangular form, and then solving it for the currents, right? So this is a method which I've described in the course, and that's what I'll go to. So as usual, before I start this lecture, a little bit of brief background that if you are interested in these kind of video lectures, but you would like something a little more comprehensive, I do have full-length online courses. For that, I'll just go over to my own website, which is pythonpowerelectronics.com. This is the homepage of this project, and this contains everything that is related to the circuit simulator, Python Power Electronics, and also all associated materials. So for example, if you go to the button Learn, you go to the list of online courses which I have at present. So the very first course is called Simulating Power Electronic Circuits Using Python, and this is the basics of how you can simulate a circuit with Python, and contains basic knowledge like how to install Python, how to use Python, how to install Python Power Electronics, and a little bit of basic background about power electronics. And finally, there is a case study how to simulate a simple buck converter. And this course is currently hosted on the MOOC website Udemy. You can click on this button to go over to the course link. Now, the next course which I have is called Basics of Digital Signal Processing for Power Engineers, and this is how, in this course I talk about how you can use Python for designing and analyzing filters. So I have a basic background on signal processing such as Laplace transform and frequency response characteristics, and eventually I have a case study how you can simulate a low pass filter and a notch filter using Python, and especially the signal package in SciPy. Again, the course is hosted on Udemy. You can click on this button to go to the course link. The third course which I have is called Simulation of Magnetics for Power Electronics Using Python, and in this I talk about how you can model and simulate magnetic components such as inductors, coupled inductors, and transformers. And finally, there is a case study of how you can simulate a flyback converter with multiple outputs using a multi-winding transformer, and also the transformer is operated at high frequency. So this course is very relevant to what I'm doing currently, which is simulating a 3-winding transformer. And if you would like to know the details of how you can solve this equation in a matrix form, check out this course, because this is where I describe it in detail. As before, it is hosted on the MOOC website Udemy, so you can click on this button to go over to the link. And the latest course I have is called Control Analysis with Python for Grid Connected Converters, and in this I talk about the basics of control systems applied to power electronics. So I talk about some basic concepts of closed loop systems. I talk about the basics of how we define and design control systems and how we define the performance of a control system. And finally, I have several case studies of how you can control, design, and implement controllers for various applications using a single phase grid connected converter. So also this course is hosted on the MOOC website Udemy, so by all means click on this link to go over to the website. So with this I will get back to my lecture. Now to complete this, all I have to do is copy these variables. I leave this as it is so that they remain in the comments. So as I already said, we have calculated the 3 currents I3, I2 and I1. So these are the currents in the 3 windings, right? So we will be first calculating I3, because I3 is only in terms of the flux linkages, and the flux linkages we have calculated above, which is the integral of the induced EMF, right? So to keep going, Once we calculate I3, we can calculate I2. And I2, we already have the expression for it above. It is this one, where I2 has been expressed in terms of I3. And of course the flux linkages. And once we calculate I2, we can also calculate I1. So we have two expressions for I1. We have an expression for I1 in terms of only I3, and we have an expression for I1 in terms of I1 and I2. We can use either of them. So let me use the first one because it's a cleaner equation. You can use either of them. It doesn't really matter. They are equivalent equations. So we now have calculated the three winding currents. What we need to do is we need to now calculate the winding voltage, and we have to calculate the winding voltage for winding 3 in exactly the same way we did for winding 2 and winding 1, which is winding 1, this winding voltage is the applied voltage. So this is the applied voltage with which we are calculating how much current needs to be supplied, and the resistance, which is the series resistance of the winding. This is not the internal resistance. This is the resistance which is connected physically. So for example, if I come over here, this is this resistance, variable resistance transformer 1. Right? So I'll just come over to winding 3. It is this one specifically. So coming back to the equation, all I have to do is change the subscripts. Right? So with this, we have completed our simulation model, and all we have to do is now go and run this simulation. So let me go over to my web browser. We are in the control configuration. We can exit, go to the main page. And go one step higher and higher again, and this is it. So let me click on the run button. The simulation is running. Always go to the command line, make sure there is no error, and there is none. Right? Now, if you are following along with this lecture and you have been solving this also, remember that these equations are extremely sensitive to all the variables. Right? You might very well have some error here related to a variable not being defined. In that case, make sure that you go and check the typo, or rather the spelling of each and every variable. Right? For example, if I make a mistake here and I put psi I, right, or here rather, this will result in a syntax error because we have not defined this variable. So in your case, if you're following along with this lecture, make sure that if you get any errors, you check your equations. I would suggest take a pencil and paper and try to solve these equations yourself. Again, if you're really serious about building a transformer model, I would not recommend you to do all this. I would recommend you to use the matrix method, and for that I would say just go over and check this third course which I have, which is simulation of magnetics for power electronics using Python. Right? If you're interested or rather serious about building transformer models. So anyway, now that we're here, this simulation will take quite a bit of time to run. So I'm going to pause the simulation and run again once the simulation, or rather restart this video when the simulation has run for quite a while. So I'll be back soon. So the simulation has been running for quite a while now, and I've stopped the simulation. So all we have to do is now go and plot some values. So since we have a transformer, the obvious plot that we can plot is, of course, we can plot all the voltages. So there's two ways we can do this. We can either plot the voltages across these windings, right? That is winding 1, winding 2, winding 3, right? But it's important to note that these are the internal voltmeters of this transformer model. Again, there's nothing wrong in plotting them. It's perfectly okay. However, what I would always say is, rather than going and plotting the voltmeters and ammeters within the transformer model, always usually it is better to plot those outside. So for example, if you look at our voltage source, we have a voltmeter Vin. This voltmeter Vin measures the voltage which is being produced, and this is the source voltage. Now this source voltage is applied to the winding 1 of the transformer. So really speaking, we are plotting the same voltage. But it's important to note that the voltmeters within the transformer have polarities that are adjusted according to what the transformer winding needs. Whereas the voltmeters that we've connected to our source is rather with respect to the source voltage. So therefore I would rather plot this instead. So this is one we would like to plot, and of course we have the two loads, so load 1 and load 2. We have voltmeter load 1 and we have voltmeter load 2. These are the two voltmeters across the two loads. So I would plot these three. So let's go over and create a plot, and I would call this voltages, and the first one would be voltmeter Vin. I would call this V1 because it's the winding 1 voltage. The second one would be voltmeter load 1. I would call this V2 because this is winding 2 voltage. And the last one is voltmeter load 2, which is V3. And let's save this voltage, save this waveform. So we have 3 voltmeters as winding 1, winding 2 and winding 3 voltage respectively. So I'm going to click on done and let's plot it. So let's go over to our file browser. And these are the voltages. So important to note that we have produced 3 voltages, right? Now of course it's very difficult to figure out what's going on. So let me zoom in between, let's say 0.6 and 0.7. So I'll put a next zoom of 0.6, or let's say 0.7 to 0.8, doesn't matter. And let's go over to the file browser and check out these voltages now. And this is what we get. So let's zoom in and figure out what's going on. So the blue line is the voltage across winding 1. The yellow or the orange line is the voltage across winding 2. And the green line is the voltage across winding 3, right? So the blue line has a peak of 340, or rather somewhere, see if you look at this, this is 200 and 300, so this is somewhere around 400, which means this is around 340. This is only expected because we have chosen the input voltage to be, chosen this input voltage to be 240 volt RMS, right? So for example, if we go over and verify for ourselves, we see that this is indeed the case, right? This voltage is 339. The reason why I chose 339 is because 339 corresponds to a peak, corresponds to an RMS voltage of 240, right? This is the peak value corresponding to an RMS of 240 and a frequency of 50 Hertz. So if we go back here and have a look, that's what it is. So this is essentially the voltage which is being produced by the source. Now let's figure out what's going on here. Now if we look at this, we see that the secondary voltage, which is the winding across winding 2, is around half of what the primary is. Now let's go find out why that is. And the reason for that is because the way we've chosen our voltage ratings, right? So we've chosen the primary to have a 240 volt rating. We've chosen the secondary to be 120 volts and the third winding also to be 120 volts. So this is a step down transformer where there is the source supplying one high voltage winding and the loads are connected to two low voltage windings. So therefore it is only expected that this orange line is half the magnitude of this blue line, right? And if I zoom in, I'll find that this magnitude is indeed half. Now let's figure out what's happening with this third winding. Now this third winding, the reason why it is so is because we have used exactly the same dot polarity as we did for the forward transform. Now if we go over to the transformer winding, we will know that in the case of the forward transformer, this third winding has a dot polarity such that the dot is at the lower terminal. And if the dot if for the winding 1 and winding 2 were in the upper terminals, the winding for the lower or third terminal is in the lower winding. So therefore, the voltage produced in this third terminal, or third winding rather, is going to be 180° out of phase with the voltages in winding 1 and winding 2. So therefore, if I look at this image again, that is exactly what we are seeing. The voltage across winding 3 has the same magnitude as that across winding 2. The reason, if you look at our editor, they have the same ratings. But because the dot polarity is reverse, this voltage has a 180° phase shift. Now, here it may not really mean much, but in the forward converter, this is very important, right? Because the forward converter, the third winding, the job of the third winding is to feed back the magnetic energy stored in the transformer back to the DC supply. So therefore, this indeed is correct operation. So now that we have done this, let us check out the currents and then let me wind up this video. So I'll go back to the output page and create another plot, right? I'll call this currents. Start the plot. And here I'm going to again plot the currents, but again I will not plot the transformer currents. I won't plot these ammeters. The reason again is these ammeters are internal to the transformer model. What I would instead plot are the ammeters that are exterior, that is, these are the ammeters. So if I want to find out what is the current in winding 1, I am going to use this ammeter Vn. And if I need to find out what are the currents in winding 2 and winding 3, I will use these ammeters, which is the current measurement in the loads itself. So let me go and add that. This is already there, so I can use it as it is. I'll call it I1. And then I can choose ammeter load 1, call this I2. Save. Ammeter load 2, call this I3. Save. So we have I1, I2, I3, right? I1, the ammeter just at the output of my voltage source. I2, the ammeter in my load current or other resistor load 1. And I3 is the ammeter of load 2, which is across winding 3. With this I'm done. And let me click on the plot button. So let's go over to the file browser and check out what is this currents. So as before, very difficult to make any sense out of this. So let me go zoom in between 0.7 and 0.8. So I will go again here, choose the X zoom 0.7 to 0.8, exactly what we had for the voltages. So let's go over to the file browser, check out currents, and now we have a much better waveform. So let's see what's going on. So first is we have this blue line, which is the current in winding 1, right? The second we have is the current in winding 2, and then we have winding 3. So now let's think a little about what's going on. Now initially there may be a lot of confusion about this particular waveform, and it may seem wrong for several reasons, and I'll go through them one by one. First and foremost, winding 1 is the high voltage winding, and winding 2 and winding 3 are the low voltage windings. So technically what we do expect is we expect the high voltage winding to have a lower current than the low voltage winding, because that's how transformers work, right? A transformer steps up the voltage or steps down the voltage and steps up the current. In our case, we have a step down transformer, which means the current will be stepped up. So what we do expect is that the current in the primary, we expect it to be less than the current in the secondary. But that's not what we are seeing here, right? To begin with, we see that this current I1 is comparable to the current in I2 and I3. Now, coming back first, let's circle back to this a little later, but first and foremost, let's look at I2 and I3 in exactly the way we saw for the voltage across winding 2 and winding 3. The current in winding 1 and winding 3 are also offset. You see there is a 180° phase shift in exactly the same way, because the dot polarity is such. We have connected winding 3 in such a way that the dot polarity is the reverse of winding 2, and therefore the current in winding 3 is 180° phase shifted from winding 2. right? So this solves one problem, that is, this is nothing wrong with it. Winding 2 and winding 3 should be phase shifted. Now coming back to winding 1, the first thing we see is that there seems to be a DC offset. Alright, because quite obviously if you look at this current I1, the positive peak is way above 10 amperes, almost close to, if this is 5 amperes, this is 10, this is probably close to 15, which means we are somewhere around 14 amperes, right? Now if we are around 14 amperes, the positive peak, and you see the negative peak is not even minus 10. So there is quite obviously a DC offset. So the first thing you might think is this is a bug. Right? This is a bug in either the software or there's a mistake in the simulation, but actually it's neither of these two. The reason is that we have used a transformer, right? Now for this let me just close this down and save this because I don't want to plot it again. I will just call this currents 1, and let me go and plot the currents for the first few cycles. So let me plot it for the first few cycles, which means let me plot around 3 cycles. I'll choose 0.06 because then it will be 3 cycles. So if I plot it for these 3 cycles, we will know why this DC offset appears. Let's go over to the file browser, and this is the new currents, and you see this is what we get. Now let's look at what's happening here. We see here that the current is a sinusoid. Alright, now this current is a sinusoid, and this has another impact which is a little difficult to explain unless you go into the depths of magnetics. In our case, we have chosen the voltage to be a sinusoid, right? Now, for example, all we have to do, if you want to know why, just go back to the main page, edit circuit parameters, voltage source, and you'll see we've chosen this voltage source, and there is no phase angle shift, which means this is a sinusoid. And if this is a sinusoid, then in that case we expect the flux linkage, which is the integral of the induced integral of the voltage, to be lagging by 180 degrees or rather 90 degrees because it's the integral. But in this case, because the flux must start at 0, the result is that there is a DC offset in the current. This is not a bug, this is a known phenomenon. When you turn on a transformer, there will be a DC offset in the current, except in the rare case when the voltage is a cosine waveform. Only when the voltage is a cosine waveform do you find that the current will have no DC offset. This DC offset is what is the DC offset in the magnetizing current of the transformer. And if we need to verify this result, let me go back to the output page, and let me go back once again to my circuit because I'd like to zoom in. So this is 10 amperes, this is 15 amperes, it's probably around 12.5 or somewhere around middle. So let us zoom in between 12.5 and 14. I would now like to capture the envelope. So I'm going to zoom in between 12.5 and 14. So let's go over to the file browser and check out this current again. And you see that we see the envelope. So here you can see the envelope of the current. And as you can see, this envelope is decreasing. The reason for this decrease is that as time progresses, the DC offset will die down. Right? This DC offset, which is the DC offset in the magnetizing current, right? This will die down with time because it is absorbed in the resistances of the transformer, right? If we do not model any resistances, they will stay constant, but eventually this will decay to 0. This is merely to do with the magnetizing current having a DC offset because the voltage is a sinusoid. This is not a bug. This is a known phenomenon, and this happens for almost any transformer that is turned on when the voltage is not a cosine. Now if we run this for a long time, we'll find that this DC offset eventually decays completely to 0 and the current will be a pure AC waveform. Right? In large transformers, sometimes this current can take minutes to die down, several minutes, because that's how large the DC offset is, and sometimes the DC offset does take a long time to settle down. Now, with this lecture has gotten already pretty long. We now have a working 3-winding transformer. Now what we're going to do, we're going to now use this 3-winding transformer in our forward converter. But before that, I'm going to have one more lecture where I'm going to simulate this at high frequencies to make sure that we have a working high frequency transformer model. And that high frequency transformer model will then be placed into our forward converter so that we can simulate the forward converter. So, as before, if you have any doubt, either post in the comments or message me on social media or send me an email, whichever is your preference. Otherwise, I will see you next week where we continue with this simulation. Thank you so much and see you soon. Goodbye for now.